Bismillah ar-Rahman ar-Rahim, and welcome to lecture number 11 for basic engineering mechanics. In this lecture we would start chapter number 4 of our book, and this chapter is about four system resultants. And in today's lecture we would be discussing the turning effect or the moment of a force, and we would first see its scalar form, then we would define what is called a cross product, and then we would use the cross product to define the vector form for the moment of a force. So let's start. What is the moment of a force? Very simply put, moment of a force is just a turning effect of a force. Here we see that anytime we apply a force on a rigid body, it would try to rotate that body as well. For example, here we can see this example of a wrench, and whenever we apply a force F, this force would try to rotate this wrench about this axis. So the definition of the moment of a force is the force times the perpendicular displacement. Anytime we have a given force and it is acted upon at any point, we measure the perpendicular distance from the axis of rotation to that point, and then we multiply the two together and we get the moment of that force. And you can already see that the units of the moment of the force are going to be Newton meters, because force has the units of newtons and distance has the units of meters. So in this first example A, the moment is just equal to F, the magnitude of the force, times the distance d. But if we look at this second picture, here the force is not acting perpendicularly on the wrench. So again, now we have to find the perpendicular distance of the force to the axis of rotation. Here the perpendicular distance is this distance d prime, and d prime is nothing but d times sine of theta. We can just use some trigonometry on this triangle and we get this result. And so the moment of the force in the B case is F times d times sine of theta. And here we have this third case where the force is acting along the axis of distance from the axis of rotation. In this case, because the perpendicular distance of the force to the axis of rotation is equal to 0, that means that this force has the moment of 0. In other words, this force will not produce any turning effect or moment about this axis. So when we define force, a force does not, to define a force we do not need any other quantity. If I talk about force applied from body A to body B, I can just talk about it. But whenever we are defining a moment, we need to define the moment along a point or about an axis. Because here we see that if here in all of these three situations we were calculating the turning effect of the force about this z axis. If we were to calculate the turning effect of this force about some other point, then the moment would also change. So this is a subtle difference between how we treat forces and how we treat moments. What about the direction and magnitude of the moment of the force? So the magnitude of the force is just F times d, as we saw earlier, where d is the perpendicular distance, and the direction of the of this moment of the force is given by the right hand rule. So we can see here that this force is trying to produce a rotation in the counterclockwise direction, and so using the right hand rule, if we curl our fingers around in the direction of rotation, then our thumb would point in the direction of the moment of that force. So we have a magnitude and we have a direction. So in two dimensions, whenever we are looking for objects in two dimensions and we are solving for forces in two dimensions, a moment can either be in clockwise direction or it can be in counterclockwise direction. So if we look at a body which is in 2 dimensions, so let's assume we have this cell phone here. It can either be rotating like this, which would be clockwise, or it could be rotating like this, which would be counterclockwise. But in 3 dimensions, we can see that this cell phone can be rotating something like this or something like this. So this phenomenon that the moment is either counterclockwise or clockwise is only found when we are looking for rotations only in 2 dimensions. And so in the 2 dimensions case, we simply use the fact that counterclockwise moments would be positive and clockwise moments would be negative. Here we can see that we have 3 forces, and each of the forces producing a moment around this point or O. This force F is producing a clockwise moment, so we already saw that the clockwise moment would be negative, but this force F1 is producing a counterclockwise moment, and this F3 is also producing a counterclockwise moment. So the resultant moment is just the sum of all the 3 moments, and it is given by F1 times D1 minus F2 times D2, because we have this force is producing a counterclockwise clockwise moment there, so that is why we will put a negative sign with it. And this third force is producing a moment which is F3 times D3, and it is positive because this is a counterclockwise moment. So here we look at some very simple examples of moments in 2 dimensions. So here we have a bar, or you can say a door when we look at a door from the top. So we want to find the moment produced by this force, 100 Newton force, about this axis O. So what is our definition of moment? Like we saw before, so the moment of a force is just the force itself times the perpendicular distance. So in this case we can see that we have this rod, there is a force F, and so the perpendicular distance is just this distance, which is given to be 2 meters. So the moment is simply equal to, and this force was actually 100 newtons. So the total moment is just 100 newtons times 2 meters. This is the F and this is T. Okay, so the total moment is just 200 Newton meter. If we want to be, if we want to assign positive or negative with this, as we were already saying that clockwise moments are defined as being negative, so we can say that this is negative moment. Another convention which is used to write moments is that sometimes we refer to as clockwise positive moment around the origin O is equal to 100 Newton. So both of these are correct. Here I have only mentioned that the moment is equal to 200 Newton meter, and I have put a negative sign. Whenever I am not mentioning if I am taking clockwise positive or counterclockwise positive, so the convention is to use counterclockwise moments as being positive. So clockwise moments would be negative. But sometimes we would write the direction up front. We would say that we are assuming that the clockwise moments are positive, and assuming that the clockwise moments are positive, the moment of this force is 200 Newton meter. So both of them are equivalent and both of them are correct. So so here we can already look at the same result that we have computed, and we have given that this with this symbol also that it is clockwise. Okay, this is another convention used. Okay, so here we look at another example. So we have a force which is 600 pounds. So let me draw this. So this was A, let me draw the second case, which is part D. Both of these are from the book, so you can just look them up also. This is something like this, okay, and then we have a 60-pound force acting in this direction. And so if I were to draw the perpendicular distance for this force, I can say that the perpendicular distance is just, so this is the axis, so this is my perpendicular distance. And we can already see in the figure that this distance is equal to 1 times sine of 45 degrees. So in this case, and this is counterclockwise movement, and so this is the origin O, so I can again say that the moment around point O is simply equal to 60 pounds times D is given in feet, so this is 1 times sine of 45 degrees feet, and this is counterclockwise, so I can put an arrow telling me that this is counterclockwise. So we can simplify this and we can say that this is equal to 60 divided by square root of 2 pound feet counterclockwise. So this is another unit for moments. We can either use Newton meters or we can use pound feet. Some of the problems would have this unit, some of them would have this unit, but I hope we are already very familiar with both of these units, so there should not be any problem. Okay, so moving on. So here we again see the same thing which I have done on the board. So we'll look at another example. So this is example from the book also. So we want to determine the resultant moment of the four forces acting on the rod shown in the figure 4-5 about the point O. So again, because we are told to compute the resultant moment, so we are told that we want to compute this resultant moment around this point O. So I will let's go through one force at a time and find out how we would calculate the resultant, the moment of that force. So first of all, let's look at this 50 Newton force. This is the easiest to calculate the moment. We can simply say that the moment of this force is 50 newtons times the perpendicular distance, and the perpendicular distance here is 2 meters. So the moment due to this force is just 50 times 2, which is 100 Newton meters. Next we look at the second force, which is 60 Newton force, and this force actually has a perpendicular distance which is 0, because this force is the line of action of the force is passing through the origin or the point O where we are trying to find the moment. So this force has no moment around this point O. Next up we look at this 20 Newton force, and the perpendicular distance of this 20 Newton force is just this distance here, and this distance is going to be equal to 3 times sine of 30 degrees, because the length is 3 and this is just sine of 30 degrees. And the fourth force, which is 40 Newton force, would have a perpendicular distance which is equal to 2 plus 2 plus 3 times cos of 30 degrees. And so this would produce a counterclockwise moment, but this would produce a clockwise moment. So let me just write it down on the board. Okay, so the total moment, resultant moment about O is equal to, so we have the first term. So again I would use this convention that I would assume that counterclockwise moments are positive. So I would say that my counterclockwise moments are positive. Okay, So in this case we would have 50 times 2 but with a negative sign. Why we have this negative sign? Because this 50 Newton force is producing a negative, is producing a clockwise moment. And then we have the second force, which is 60, but the perpendicular distance is 0, so this will produce no moment. And then we have the third force, which is just 20 times 3 sine of 30 degrees. And so this force is also going to be, this moment is going to be counterclockwise, so that is why this is positive. Okay, and then we have the fourth force, which is 40 times 2 plus 2 plus 3 cos of 30 degrees. So we can sum them all up and we get the total moment. As you can already see here, we have all these terms, and at the end we get a negative number. So here it is mentioned exactly like I did on the board, so that counterclockwise moments are positive and the resultant moment about the point O is just sum of all the moments, and we calculate all of these moments, and so the resultant moment comes out to be negative, which basically means that the resultant moment was in counterclockwise direction. Okay, so the important take home message is how to understand what is the perpendicular distance of the force. So another easy way to find that is if we draw a line of action of the force, a very long line, then we have to draw a perpendicular from that line to the origin, and that distance is the perpendicular distance. Okay. So the next topic we are going to cover today is that of a cross product. I would cover this topic rather hastily, assuming that you have already gone through this topic when you were in your high school. Okay, so a cross product is also known as a vector product. So a cross product takes in two vectors. So A crossed with B, so vector A when crossed with vector B gives another vector, which here we have labeled as C. So this when we read it, we would say C equals A cross B, but we understand that all of these three are forces, are vectors rather than scalars. Okay, and so the basic properties of a cross product. A cross product can be defined in many different ways, but the way that we are trying to use to define the cross product is to say that the magnitude of the cross product is given by AB times sine of theta. So the magnitude of A times the magnitude of B times the angle between them, and theta is the angle between these two vectors. Okay, and the direction of this vector C, so this gives the magnitude of that vector, and the direction of this vector is given by the right hand rule, so that if I curl my fingers from vector A to vector B, so my thumb points in the direction of vector C. Okay, so we can already understand a few properties that we'll discuss later. So when we write this vector C as a vector, so here we have its magnitude, and magnitude is given by AB times sine of theta, and the direction of this vector is given by the right hand rule, and which is given by this unit vector, which is pointing in the thumb direction once we curl our right hand fingers from vector A towards vector B. Okay, so what are the basic operations or basic rules of operation for the cross product? The first one and the most important and common one is that it is anti-commutative, which basically means that the cross product of A cross B is equal to minus B cross A, and this can be very easily understood using this definition of direction, that I have to curl my fingers from A to B, then my thumb would point upwards. But if I had B cross A and I curl my fingers from so if A cross B is something like this, if I curl my fingers from B cross A, so my direction of the thumb would be opposite, so the vector would be negative. So that is why we the cross product is not commutative, it is anti-commutative. The second, this is very trivial to prove, that any times we multiply a cross product of two vectors with a scalar, so the scalar can either be multiplied by the first vector, or it could be multiplied with the second vector, or it can be multiplied at the end. It doesn't really matter. So the cross product is associative with respect to scalars. Okay, and cross product is also distributive under addition, which basically means that if I'm taking a cross product of a vector A with two vectors B and D, the sum of these two vectors, it is equal to if I cross A with B first and A with D first, and then I add the two. So it doesn't matter if I add them first and then take the cross product, or take the cross product first and then add them. So these two are equivalent. So this property would be known as that cross product is distributive under vector addition. Okay, so most of the times when we'll be using cross product, we'll be using them on Cartesian vectors. So it is important to understand that how these cross products behave under the Cartesian vectors. Okay, so a few important things, because all of these Cartesian vectors, we can write all of these Cartesian vectors into three unit vectors, I hat, j hat and k hat. So if we know how this cross product behaves on these three unit vectors, that gives us a very good idea of how this cross product would behave in any general Cartesian vector. Okay, so let me just use the board here for a little bit. So I draw these three axes. So this is my x axis, this is my y axis, and this is my z axis. Okay, so I already know that my I hat vector is pointing in this direction, my j hat vector, so this has to be straight, is pointing in this direction, and k hat vector is pointing in this direction. So this does not follow the right hand rule, so this has to be x and this has to be y. Remember in lecture number 2, I think, of this course, we discussed that how we only use right hand coordinates always in this course and in the rest of engineering and in the rest of our lives also. Okay, so here we see this is the three unit vectors. So first of all, I want to compute I cross j. Okay, so this angle, of course, we know that this angle is 90 degrees. So if I curl my fingers from vector I to vector j, I can see that my my thumb would be pointing in the k hat direction. So this is going to be k hat. So the next up, let me just do j cross k. So if I curl my fingers from vector j to k, then this will be I hat. Okay, and I also know that the unit, so this magnitude part we also have to figure out. All of these vectors are unit vectors, which means that if I were to write it more clearly, so I would have the magnitude of I cross j here and then the unit vector k. But what is the magnitude of I cross j? I already know that the magnitude of the cross vector is just equal to the magnitude of the first vector times the magnitude of the second vector times sine of the angle between them. And so what is the magnitude of the first vector? This is 1, second vector is 1, and sine of theta, the theta between these two vectors is 90 degrees. Sine of theta is just 1, and so this is 1. So here that is why we get k hat. And similarly for all of the others. Let's do one more. And so we have done I cross j, we have done j cross k. Let's just do I cross j, I cross k. Okay, so when we do I cross k, so I have to curl my fingers from I towards k. So I can already see that the unit vector is going to be known as j hat. direction. Okay. So these are the basic operations, and because using the anti-commutative property we can already figure out the other three. Important thing, and one more thing to note, is whenever we do the cross product of two unit vectors which are the same, so I cross I, this is going to be 0. Why? Because anytime we are choosing the same vectors, the angle between them is 0 and sine of 0 is 0, which means the magnitude is going to be 0. So I cross I is equal to 0, j cross j is equal to 0, and k cross k is equal to 0. So this completes our Cartesian vector formulation. So basically, anytime I have two vectors, vector A, which is given by ax I hat plus ay k hat j hat and az k hat, then you can easily derive this result. And this result is very easily summarized using this matrix. So here if we write a matrix where I hat, j hat and k hat are on the top, and then we write ax, ay, az, by, bx, by, bz. So this, the cross product of these two vectors is just the determinant of this matrix. Okay, so moving on, now we want to relate cross products to moments. So the moment of a force is just the r vector, and r vector is the position vector from the origin or the point from where we want to find the moment to the point of action of the force. And secondly, F is the force itself, and so the moment of the vector for moment of the force around the point O is equal to the position vector from point O to point A, which is the point of action of force, crossed with the force itself. And it's very easy to prove why this formula is correct. First of all, we look at the magnitude part, and the magnitude part, as we already saw, that for the cross product the magnitude is just the magnitude of the first times the magnitude of the second times the angle between them. So here in this diagram we can see that the angle here is theta and the magnitude is r and f, so we get r f sine of theta. But we can quickly see that r times sine of theta is just this distance d, which is the perpendicular distance. So at least the magnitude part of this definition of the moment of the force is the same as our previous definition. The second is the direction part, and we already know that the direction is given by the thumb rule in this case, and it was given using the same rule when we were using the scalar form of the moments. Okay. Let's look at another important principle for moments, which is called the principle of transmissibility, which basically means that a force, whenever we want to compute the moment of a force around any point O, so we have the liberty to choose from many different position vectors. So we can choose any position vector along the line of action of the force, and we would still get the same moments. So again, it is very, very easy to prove. So the moment of this force around this point O can either be written as r1 times f, or it can be written as r2 times f, or it can be written as r3 times f, or any other position vector from point O on the line of action of this force f. And it's very, very easy to prove also. And so basically this implies that the force F can be considered as a sliding vector. So this force can be moved up and down on this line of action of the force, and it would still produce the same turning effect or same moment. Okay. So the proof is very, very simple. So let's assume that R2 can just be written as R1 plus R21, and R21 is just the position vector from vector R2 this end to this end. So R2 cross F can be written as R1 plus R21 cross F, which can be written as R1 cross F plus R21 cross F. But this part R21 is in the direction of the force itself. So we know that R21 cross F is going to be equal to 0, which means that R2 cross F is going to be equal to R1 cross F. Very simple to prove, but very important when we are solving for moments. Okay, so the Cartesian vector formulation, as we have already seen, is that the moment is equal to the position vector times the force, and the position vector is measured from the point of where we are calculating the moment to the point of action of the force. And so we can draw meanings to each of the term of this in this force. So let's draw a few of them so that you can get some idea. So any force can be broken down into its x, y and z components. So here we see that we have broken down this force F into its x component. So this is supposed to be Fx, then this is Fy, and this is Fc. So this Fx would try to rotate this along the z axis. Okay, this would try to produce a rotation along the z axis, and it would also try to produce a rotation along the y axis. So here we see that we have this Fx term which is trying to produce a rotation along the j axis, which is the y axis, and we also have this Fx term which is trying to produce a rotation along the z axis. Okay, so now we get to the crux of all of this. So whenever we are trying to find the moment of the resultant moment of many different forces which are acting on any rigid body, so then we have to sum up all of the individual moments which are produced by all of these forces. So in this case we have these three forces, and so we would just find the moments due to all of these three forces. We would add up all of these moments and we'll get the resultant moment. This is very similar to what we did for the forces. So the resultant force on any body is equal to the sum of all the forces acting on that body. Similarly, the resultant moment on that body is equal to the sum of all the individual moments acting on that body. Okay, so here we have we will look at two examples about the moment of the force. I would sketch the procedure of solving these examples here, but we would discuss more about them in the live class. Okay, so we have this tractor which is trying to pull this on this tree at point A, and so with a force of 2 kilonewtons, which is directed along this position vector UAB. So we want to determine the moment produced by the force F in figure 4-14A about the point O, and we want to express the result as a Cartesian vector. So to find the moment about the point O, what are the two things that we need? First of all, we need the r vector, and then we need the f vector. So let me just sketch the result. Okay, so as you can already see that r vector so is the vector from this point O to point A. So I can simply say that my r vector in this case is just equal to 12 k hat. So my moment on the point O is going to be equal to r cross f. And so r vector was easy enough. So the vector r is just 12 k hat. It is in the z direction. So what is the force F? Force F is equal to the magnitude, which is 2 kilonewton, times the unit vector along AB. And we have dealt with unit vectors many times over our discussion. So I would just write the unit vector down. So it is 2 kilonewton, and so the unit vector is just the position vector divided by its magnitude. So let me just write the position vector, which is just 12 I hat plus 4. No, actually, sorry, it has to be 4 I hat plus 12 j hat minus 12 k hat. Okay, and so now we have to divide the magnitude of this whole thing, which is just equal to 12 square plus 12 square plus 4 square. Okay, so this is the form. This is the vector force vector, and this is the position vector. We can plug in these two in here to find the moment. Okay. So here I have already attached the solution in these slides. You can have a look at them also. So here we look at this other example. Again, I would sketch how this is solved, and we will solve them in more detail in live lecture. Okay. So we have these two forces acting on this rod, and we want to find the resultant moment. Nothing very fancy here. Both of the forces are already given, and the Cartesian vector form is already given. The only thing we have to do is to find the r vector. So in this case is in the force F1, the r vector is very trivial. This is just 5 j hat. Okay. The r vector for F2 is also not very difficult. It is just 4 I hat plus 5 j hat minus 2 k hat, and then we use those two r vectors and these two forces to find the resultant. Okay. So here I have attached the solutions also in these slides. You can have a look at them. So that is it for today, and I will see you in the next lecture, inshallah.